Nitte Meenakshi Institute of Technology, popularly known as NMIT.
Hi everyone, we are in the Aerodynamics Lab of the Department of Aeronautical Engineering, Nitte Meenakshi Institute of Technology, Bangalore. So our wind tunnel facility has various measurement techniques like the velocity, pressure, the force and the few visualization techniques where we are able to gather the aerodynamic characteristics around the object of interest. So here today we will be discussing how the measurement of velocity can be done. We need to know the velocity inside the test section. So the measurement of velocity inside the low speed subsonic wind tunnel can be calculated by using the Pitot-static probe. So basically it works on the principle of Bernoulli, and it is basically the low speed subsonic wind tunnel. So the velocity in the test section, it is in the range of 0 to 50 meter per second. So the Bernoulli's equation can be applied to calculate the velocity inside the test section. So when it comes to the calibration technique, so we have the technique for measurement of velocity and plotting the graph with the speed of the motor, because as the speed of the motor changes, the mass flow rate inside the tunnel changes, so the velocity of the flow inside the test section or the tunnel will be changing according to the speed of the motor. So here we will be calculating the velocity at different speeds of the axial motor, so that we can plot the velocity versus the speed of the axial motor, so that there will be a linear increase in velocity with the speed of the axial motor, and that will be but you can get the straight line, that is linear increase in the velocity with respect to speed of the motor. As we know that the low speed subsonic wind tunnel is working based on the principle of Bernoulli. The Bernoulli's equation states that when there is a increase in the pressure of the flow and there will be a decrease in the velocity of the flow. That means the static pressure plus the dynamic pressure will be equal to the total pressure. So to balance the equation, when there is a rise in the static pressure, there will be a decrease in the dynamic pressure. So here the Pitot-static probe, which we use for the measurement of velocity inside the test section, so we'll be working based on the Bernoulli's principle. So in the Pitot tube, we will be able to measure the total pressure, and the static probe will be helpful in measuring the static pressure of the flow. So with this difference, we can calculate the dynamic pressure of the flow. So from that, the velocity can be calculated. So now we'll discuss that how basically the Pitot-static probe works and how the Bernoulli's principle can be applied to get the velocity from the Pitot-static probe.
So now we'll discuss how the pitot tube works. We know that pitot tube is used to measure the total velocity of the flow in the airplanes. When you consider a flow with a pressure P1 moving with a velocity V1, the static pressure is a measure of purely random motion of the molecules in the gas. When you consider a boundary of the flow such as wall, there is a small hole drilled perpendicular to the surface. The plane of the hole is parallel to the flow as shown here. In this case it is point A. The pressure felt at point A, because the flow moves over the opening. This is due to the random motion of the molecules. That is, at point A the static pressure is measured using static pressure tap. When the pitot tube is inserted into the flow with the open end facing directly into the flow and the other end of the pitot tube is connected to the pressure gauge point C. When the pitot tube is in the flow, gas will rush into the open end and will fill the tube, and the gas inside the tube will stagnate. That is, the gas velocity inside the tube will go to zero. That is including at point P. So this point is now called as stagnation point, and the pressure at this particular point is called as stagnation pressure or the total pressure P naught. The pressure gauge at C reads the same pressure, so this measurement along with the measurement of static pressure P1 at point A will yield the difference between the total pressure and the static pressure, which is P0 minus P1. So when we incorporate the static probe into the pitot tube, that becomes the pitot-static probe. So the measurement of total pressure P0 exerted by the flow at the tube, that is at the inlet point B, and the velocity is zero at the same point. Measurement of static pressure at point A, that is P1, and velocity will be V1. So now apply the Bernoulli's equation. When we apply the Bernoulli's equation, we are comparing the properties at two different points. Here we know that P1, V1 are the properties at point A, and at point B it is P0 and V is equal to 0. Bernoulli's equation is P plus half rho V square is equal to constant. Substituting the values for two different locations, you can yield the equation to calculate the velocity of the flow by calculating the difference between total pressure and the static pressure, and rho is the density of the flow of our air at that particular altitude. Also we know that P is equal to rho gh, so the equation will reduce to root of 2 rho g into delta h. So delta h is the manometer head.
So here the Pitot-static probe is being fixed inside the test section of this low speed subsonic wind tunnel. So basically we have placed the Pitot-static probe to measure the total pressure and the static pressure of the flow, and here it is near to the entry of the test section and it is beyond the boundary layer effects. And the Pitot-static probe, internally it will be connected to the U2 manometer to get the manometer head. So this is a typical Pitot-static probe. The same kind of Pitot-static probe is being fixed inside the tunnel. So here we can see that there is a one hole, so which is at the mouth of the Pitot-static probe, and this mouth, at this particular mouth, we can measure the total pressure, and there are two holes which are drilled holes perpendicular to the flow direction or this particular Pitot-static probe. So here you can see that these two holes will be able to measure the static pressure of the flow. Internally they are extended outside, so to connect these ports to the Pitot-static probe, as I said, has the two openings. Vertically it is connected to the total pressure side and the horizontal one is connected to the static pressure side. So we are using the flexible tubes to connect that to the U2 manometer. So we have connected here and it is internally connected to the U2 manometer to get the manometric head. So here we are using the water as manometer liquid. So then other liquids like mercury and other liquids can be utilized for the application in the different manometers here. So now the total pressure side, it is connected on to this side, that is the right side of the U2 manometer. Then the static pressure side is connected to the left side of the U2 manometer. So now they are at the same level. Once we make the flow inside the tunnel, so we'll get the manometer head. So the total pressure measurement and the static pressure measurement can be done by using the U2 manometer. So here the U2 manometer is connected to the total pressure side and the static pressure side. So initially when there is no flow inside the tunnel, so both the manometer, like both the side, the manometer level will be same. So when we make the flow inside the tunnel, so due to the pressure difference, that is the difference between the total pressure and the static pressure, we can see some manometric head here. That means the total pressure side will go down because the air will be going inside the Pitot-static probe and become stagnant. So that is the stagnant pressure that can be measured at the mouth of the Pitot-static probe. So then the static pressure side will go up, so that whatever the manometric head is there, that can be utilized to calculate the pressure difference using the U2 manometer. And we discussed the Bernoulli's equation, so that the velocity can be measured by calculating the pressure difference using U2 manometer. So then the pressure difference values can be substituted into Bernoulli's equation to get the velocity inside the tunnel. So here we have the velocity indicator, as well as the indicator will be able to show the manometric head. So here the top display will give the velocity measurement in meter per second, and the bottom one will give the manometer head in millimeters. So instead of measuring or counting the manometric head in the U2 manometer, so we have the facility to get the manometric directly onto the indicator here. And here we have the speed indicator. So this shows the axial fan speed. So now the tunnel is at the static condition, that is there is no flow inside the tunnel. So now we are going to start the axial fan, so that as we increase the speed of the motor, so we can see that increase in the velocity of the flow inside the test section of the tunnel. So the calibration method what we use here, so as there is an increase in the speed of the axial fan, there will be increase in the velocity. So now we are going to plot the graph velocity versus speed, so that there will be a linear increase in the velocity with respect to the speed. So if there is a change, if there is a deviation, or if it is not a straight line, so then we can assume that there will be a problems like the leakages, or there is a turbulence in the flow. So we need to rectify those problems. So once it is done, once we get the straight line, so we can say that wind tunnel is calibrated. So to switch on the axial fan, we have the green button, and to stop we have the red, and we have the regulator to change the speed of the axial fan. So now we'll switch on the axial fan, and using the regulator we can change the speed of the axial fan. So here you can see that as we change the speed of the axial fan, so there you can see that we are just making the flow inside the tunnel. So now we are conducting the experiment on calibration, and make sure that there are no objects inside the test section while conducting this particular experiment. And it is airtight, that means there should not be any air gaps, so that the air should not enter into the test section from the atmosphere. So now you can see that the axial fan is at the static condition, that is it is at 0 rpm. So zero velocity inside that section, that means no flow inside the tunnel. So now we are just making the flow inside the tunnel by rotating the axial fan with a certain RPM. So switch it on, using the regulator button, increase or decrease the speed. So now I am just adjusting it to the 250 RPM or 273 RPM. So now you can see that there is a change in the velocity, that is from 0 to 5.9 meter per second, and the corresponding manometer head is 2.1 mm. So like that, as you keep on increase the speed of the axial fan, you can see that there is a increase in the velocity inside the tunnel. So there should be a gradual increase in the velocity as we increase the axial fan speed gradually. So the operating velocity is from 0 to 50 meter per second. So now we are just increasing the velocity inside the tunnel by increasing the speed of the axial fan.
This is the tabular column which we use to calculate the velocity of the flow inside the test section of the tunnel. So here we can take the readings, axial fan speed in RPM, velocity from the panel, and the manometer head from the panel. So the velocity from the Bernoulli's equation, which is here noted as v experimental in meter per second, can be calculated, and the error, which is the difference between v panel and the v experiment, can be calculated. So once there is no flow inside the tunnel, so zero motor speed, so the zero velocity inside the tunnel. So next I'll set for certain RPM. So axial fan has the speed of 99 RPM. So the corresponding velocity inside the test section of the tunnel is 1.9. Manometer head is 0.2. So here the velocity calculated from the Bernoulli's equation is equal to 1.9. So in this case error value will be 0. So like that I should set for the different axial fan speeds and take the readings from the panels and calculate the velocity. So then we can plot the velocity versus motor speed. So here you can see that there is a gradual increase in the velocity with respect to increase in the axial fan speed. So since it is a linear increase, the wind tunnel is calibrated now.
Okay, so today we have conducted the experiment on the calibration of the low speed subsonic wind tunnel. So now we have the data like when we set the particular axial fan speed, what will be the velocity of the flow inside the tunnel. So these values will be helpful for conducting the further experiments in the low speed subsonic wind tunnel. So hope you enjoyed the video and gathered some information about the calibration techniques in the low speed subsonic wind tunnel. So for more videos related to the different aspects of aeronautical and aerospace engineering, so you can subscribe to our channel in NMIT Department of Aeronautical Engineering. Please like, share and subscribe and click the bell icon for more videos. Thank you.